Okay. Yeah, so for those who can't watch the 3 blue 1 brown video, I have put this in the other video sections. Okay, so and along the I put the interesting things I can find on the YouTube lah. So the 3 blue 1 brown just now is over here, and also another 3 blue 1 brown, but this one is hosted in Minute Physics channel. He talks about Feynman's laws lecture, and then later also will be relevant because later we'll be talking about the rocket equation. So there's gonna be this video is also from YouTube. Is talking about how the Saturn V rocket of Apollo works, and some other videos. So this one is about the pendulum. So yeah, so if there's a chance, if there is time, I will try to yeah, copyright, so don't tell anyone. Yeah, so besides this method, right, is there any other way for students in China to watch 3 blue 1 brown? This one I don't know. So yeah, VPN, that's the only way, right? Yeah, I guess so. That means use VPN to go into YouTube lah. And that means there's no other platform. There's no other platform in hosting 3 blue 1 brown. Okay. Yeah. So besides that, okay. Let me. Yeah. So I posted the announcement about our quiz, and our midterm exam plans is here. And then yeah, this Friday I have a public talk. So our quiz, we'll be covering chapters 1 to 3, and then our midterm exam will be covering chapters 1 to 5. Okay, so yeah. Then so okay, so these are the things to show you before we start the class. So for today, let us get started with today's class now. So everyone is here. I'm recording. Okay, most people are here already, and OBS is recording. Okay, so I will go full screen. Okay, so let's continue. Right, this is a short part, which is to solve an example of a collisions in 2 dimensions, because what we have been doing so far, right? What we've been doing so far is to consider collision in 1 dimension only, and the main reason is the easiest case. We just need to understand the concept, but we need to remember as well that momentum is a vector, right? Is a rate of change of momentum is the force, which is also a vector. So collisions also happen in different directions besides just the x-axis. So but there's nothing much to add about 2-dimension or 3-dimensional collisions. It's just that you need to include the other directions as well. So we have collisions. So for example, right, if I want to solve a problem about 2 objects colliding in 2 dimensions, then we just have the what do you say, the vector form of the conservation of momentum equations. Okay, so pretty much that's about it. Right, so so then yeah, so that is the main gist of the collisions. So there's nothing much to add, so we can immediately jump to the example. We are going to solve this example 4.4.1. Okay, it is a billiard ball, right? So billiard ball is a typical, the most common type of collisions that we probably see everyday life, because billiard ball, the surfaces are approximately smooth, and they collide almost elastically. So this is a problem where we have 2 balls on a frictional surface. Ball A, or number 1, has an initial velocity 4 meters per second going to the right, and then after colliding, is going in speed 2 meters per second, and the direction is unknown. And then the ball B is initially at rest. Okay, so when you play billiard, you want to hit this is probably the white ball hitting this with another ball, right? So we want to find the final speed and the final angles. So how do we solve this type of problem? Okay, so well, let us write down the equations for the information given. Firstly, the ball A, right, I'll just write 1 because A is very messy to write on paper. as a subscript especially. But basically the initial velocity of ball A is traveling purely to the right at 4 meters per second. So I'll just say 4I, right? And then the ball B, which I label as number 2 here, is just 0. Okay, and then mass of the first ball is 0.5 kg. The mass of the second ball is 0.30 kg. So I'm not actually sure that in real billiards all the balls are supposed to be the same mass, right? So I'm not sure. But now the next thing that we want to figure out is, well, what happens after they collide, right? So after collision, right, according to the diagram given in the question, ball A, well, we give this picture, right, and it's traveling at some unknown angle, but the speed we know. So the speed is 2, right? So 2 meters per second. And then the second ball is ball B is going in some unknown direction. So we don't know, and we also don't know the speed. So we have 3 unknowns here. Okay, so we have 3 unknowns here, but what we can do is we can first write down the equation for the velocity. So the velocity after collision, right, is what? Well, if I put this, because the way I put this is my x-axis pointing to the right, therefore my velocity here is 2. So I can resolve this horizontally is 2 cos alpha and then 2 sin alpha, right? And then for this one, we don't know. Okay, so it's in terms of beta and the speed we don't know. So we can say that it is v2 cos beta going in the I direction, but this is going under the x-axis, going downwards, right? So I got minus v2, okay, sine beta j. All right, so then we can plug this into the equation, and then we try to solve this. Okay, so let's try to solve this. Well, this is an elastic collision, right? So for elastic collision, kinetic energy is conserved. Okay, so the kinetic energy is conserved. So we can start by considering the kinetic energy. So the initial kinetic energy is half m1, the speed 1 square, so the speed is 4, and then half m2 u2 square, so this speed is 0, and then after colliding they will have the final kinetic energy is, this one we know is 2, and then after colliding the final kinetic energy is, this one is unknown, but already we can already get v2 straight away, so that's very good, right? So what we have here is this, m1 is 0.5, so I got 0.5, and then 4 square is 16, right? And then over here is 0.5 again, and then I have 2 squared, so I get a 4, and then m2 is 0.3, right? So what I can do is I can times 2 times v2 squared. So what I can do is I can times 2 both sides of the equation, so I will get 16, and then 4 plus 0.6 v2 squared. So then yeah, so the rest is algebra, but basically you just want to solve for v2, right? So solving for v2, I get 4.47 meters per second, right? So I shouldn't waste time thinking about how to move this. So everyone knows how to go from here to here, right? So I got v2 already, so that's very good already. What remains is to determine the final directions, right? So to get the final directions, well, let's look at the momentum. Okay, so the initial momentum is here, the final momentum is here. So we look at the well, let's look at components by components. That is less messy. So let's look at the horizontal direction. Okay, so for the horizontal directions, right, the horizontal is here, so m times this, m times the speed is 0.5, right, and then 4, and then after colliding is m1 v1 in the x direction, so I got 0.5, and then I got 2 cos alpha in the horizontal direction, and then this one has a horizontal component as well, so I got 0.3, and then 2 sin alpha, 2 sin beta, sorry, I'm talking about this, right? So I got this. Okay, so if I simplify this, I get 2 is equals to cos alpha plus 0.3 there's a v, right? There's a v, there's a speed. Hang on, why I keep confusing myself. This is v2 sine beta. Okay, so v2 sine beta is what? So v2 sine beta is, we have found v2 already, so 4.47 sine beta, right? So if I simplify this equation, just expand this out, so I got 2 is equals to cos alpha plus 1.341 cos beta. Still wrong. Okay, it's cos beta. Yeah, I'm sorry, cos beta. Right, we're talking about the horizontal components here. Okay, yeah. Okay, so everything is correct now. Then let's look at the vertical. So for the vertical direction, initially there is no vertical component, right? Everyone is moving horizontally. Therefore, initially there's zero momentum in the vertical direction. Okay, and then after colliding is m1 times the vertical velocity. So it's 0.5 and then 2 sine alpha. And for the second object, I got the mass, and then the velocity is minus v2 sine beta, and we know v2, so we plug in the values that we know. This times this is just the sine alpha, and then this times this is hang on, minus 1.341 sine beta. Okay, so this is equation 2, right? So the rest is just solving for the two unknowns. Okay, because I found out v2 already, I just don't know alpha and beta. So two unknowns and I have two equations, so probably I can get the answer, right? So let's do that. Okay, so page 2. Okay, so what you can do is, you can well, the first thing you can do is let's rearrange a bit, right? Rearranging 1 and 2. Okay, so basically I just want to move this over. So I got 2 cos alpha is equals to 1.341 cos beta, and then this one I bring this over as well. I got sine alpha is equals to 1.341 sine beta. Okay, so my two equations become like this, and then the next thing I want to do is, well, how do I solve this, right? I have two unknowns, but they are inside trig functions. Although what you can do is this, you notice that on the right hand side there's sine beta and cos beta with the same coefficients. Okay, so what you can do is you can square both sides. Why do you want to square both sides? So you can make a cosine square and a sine square. If I make cosine plus sine square, you add them up, they will disappear, right? They'll become 1. So so that is what our plan is. So the first equation, when you square both sides, is 4 plus 4 cos alpha plus cos square alpha, and then on the right hand side is 1.341 square cos square beta, and then this one is just sine square alpha equals to 1.341 square sine square beta, right? So I got this pair now, then I just add up both equations. In fact, this part will also disappear, so I got 4 minus 4 cos alpha, and then I got 1.341 square. This plus this just becomes 1, right? So from here we can find that 4 cos alpha is equals to 4 minus 1.341 square. Just solving for alpha, you can get 36.9 degrees. Okay, so that's the job is done, right? So once you find alpha, you plug this here, you can get beta as well, right? So no problem after that. Okay, so does anyone have any question about this? Okay. Okay, so okay. So if everything, so what's beta? I didn't write, I don't copy down the numbers. The beta is 26.6 degrees. Okay, so 26.6 degrees. So this is how we predict the final directions of the particle. right? So the conservation of momentum, right, is like, especially in 2D and 3D, is actually is being used like all the time in research. And if you're at all familiar, if you heard of those particle accelerator, right, the big ones in Switzerland, okay, so their job is to discover new particles, and what they do is, well, they use conservation of momentum, basically, right? They solve all these collision problems, and then they try to discover the new particles that way. Yep, CERN. So CERN is the name of the institute, right? The biggest collider is the LHC, Large Hadron Collider. So, okay, so the problem is, like, you want to collide particles like atoms and electrons to discover new types of particles. And because there are new types of particles, right, we don't know their properties. And if we don't know their properties, we do not know how to detect them. Okay? So what they do is they collide two particles, and then momentum is conserved. So they see the output of the particles after collision, then they calculate. Then from that, you can identify a missing mass that is not observed by the detector. And then that is how they will infer the discovery of a new particle. So I believe neutron was discovered that way in the first place, if I remember correctly. Because for particles, right, it's easy to detect charged particles using the cloud chamber. Neutron is neutral, you can't detect them, right? So then they first realize the presence of neutron is by like colliding them, and then they see something is missing, it's not detected. So CERN is one of the biggest particle accelerator institute in Europe. So in US there's a few, right? Stanford Linear Collider, and yeah, I can't remember the others. Okay, so that is basically the collisions in 2D. So now we want to go to the next topic, which is to talk about the rocket propulsion. So maybe I will show you that video in the break time, but what we want to do now is to use the concept of momentum to derive the rocket equation. Okay, so this is our next topic that we want to deal with, 4.5, rocket propulsion. Okay, so what's the deal with rocket, right? Rocket is something that you it looks like this lah. This is the Saturn V rocket. Let me pull this up for the OBS. Okay, so a rocket is something that will burn some fuel, okay, and as it burns the fuel, it will eject fuel out from the back, and as it ejects out from the back, right, it will create a pushing force that will push the rocket up, and this is how a rocket can be launched into space, right? So you need this mechanism to fly into space, because you cannot fly into space using the aeroplane. Aeroplane is you use the wings, right? For wings to work, you need air, but in space there's no air. So the only way you can do this is the rocket. And by the way, about the assignment, right, the first question is that another way besides rocket is using the space elevator. So it might be interesting to look into that as well. But in any case, we want to work out how does the rocket work, right? So rocket will eject all this stuff at the back. It has some mass, okay, and if it eject at such a high quantity and high velocity, there's going to be momentum coming down this way, okay? But initially the system is at rest, so the initial momentum is 0. So if you start to eject this from the back, then to conserve momentum, right, there must be some momentum to the front, and this is carried by the rocket. So this is how the rocket will function. Okay, so this is what we want to do as well. Okay, so let's try to work out how does the rocket work. Okay, so let's see. Now to see, the first thing about the rocket is how it works, right? So let me write this down. A rocket ejects fuel at velocity. If I take the rocket's front to be the positive axis, then behind it is the negative direction. So the velocity will be negative of the magnitude VEX relative to the rocket. Okay, so this is where relative velocity will start to come in. because when when engineer design rockets, right? So what they can do, the best they can do is they can determine the velocity relative to the rocket, right? It's not relative to the Earth or to the ground or to the rest of space. Okay, so what happens here is basically this. Okay, so let's say I have a rocket. Okay, so initially it's at this state, and all the fuel is stored inside, right? So all the fuel is stored inside, and then initially it has some total mass m, and then it's initially moving at the velocity v, okay? And then 1 instant later, it has ejected the fuel out, okay? And then it will continue to move forward, right? So after this happens, well, the mass of the rocket will become a new mass. So this is a system where the rocket doesn't have constant mass, right? And the fuel will have some mass as well. So let's call this m2, okay? And after being ejected, the fuel will be traveling at some velocity relative to the Earth, okay? So all these velocities here are given relative to the Earth, and then there's a velocity of the rocket relative to the Earth as well, okay? So what we are going to do is I'm going to apply the conservation of momentum, and I can actually derive the velocity of the rocket as a function of mass. As you can see, as the rocket burns up more and more fuel, it will go faster and faster, and we can do that by considering the conservation of momentum. So how to do that? Well, we need to find the formula for m1, m2, v1 and v2, okay? So let's try to do that. Let's start with v1. Okay, so let's try to determine how to get v1. Okay, so determining v1. Okay, so v1 is the velocity relative to the Earth. What we do know is the velocity of the fuel relative to the rocket, so we need to use the relative velocity equation. Okay, so we are going to take P as my fuel. Remember, relative velocity, B as my rocket frame, and A shall be the relative to the Earth. Okay, so that means I will use the formula VPA is equal to VPB plus VBA, right? Okay, so I got this now, and yeah, so let's work this out, right? So VPA is the velocity of the fuel relative to the Earth. This is what we are looking for. So this is V1. Okay, and then VPB is the velocity of the fuel relative to the rocket, which is negative VEX. EX means exhaust, is the exhaust velocity. Okay. Wow. What's this? Okay. Yes, looks like a tiny rocket. Sugar rocket, you say. And then VBA is the velocity of the B relative to A, so rocket relative to the Earth. So this is actually, this is not V2, sorry, this is V1. Not V1, this is V, right? Because the ejection happens when the rocket is still moving at V, right? V2 is later, after he's being ejected already. So we put this as V over here. Okay, so we got V1 now basically. So V1 is, just to make it look nice, let's put this V in front. So I got V minus VEX. Okay, so yeah. Okay, so that is V1, right? Then wait, let me hang on. Let me get some paper. I'm running out of paper. Okay, so yeah, where were we? So we have found V1 already, and how to get V2? sorry, my also need pen. Okay, so my V1 is just V minus VEX. So I determine V1 here. How about V2? So that's our next thing to do, right? So determining V2. Okay, so how to get V2 now? Well, to get V2, right, V2 is the speed of the main chunk of the rocket, okay, and this V was still the rocket before ejecting the fuel. So from here to here, it has experienced a change in velocity, right? So what I'm going to do is I'm going to let the change in rocket velocity be delta V. Okay, so delta V is just the final minus the initial, right? So this is the later speed, this is the initial speed, later velocity, the initial velocity, right? So this is delta V. So that means I can express V2 in terms of the previous V plus delta V. Okay, so from this equation we see that if V2 is a higher velocity than V, that means delta V is a negative quantity. Okay, so we expect delta V to be a negative quantity, right? So positive quantity, right? If V2 is higher than V. Okay, so that is V2. So we got V2 already. So let's put this here. Okay, next is to determine M2. Okay. So yeah, sugar as fuel. Charles, explain what the V2 Oh, V2 is actually so V2 is the change in the rocket velocity, right? Not V2. So the change in rocket velocity is delta V, right? So delta V is the final velocity minus initial velocity. The final velocity is V2. So actually I'm not really doing much. I'm just writing V2 in terms of initial velocity plus the change. So that's about it. Okay. Yeah, I guess you can make a rocket using Mentos and Coke as well. Okay. Basically you just put a bottle and liquid and somehow give it a high pressure using Mentos or something, and it will shoot out and it will become a rocket. So next is to determine M2, right? So how to get M2? M2 is this. Same thing. I'm going to let delta M be the change in rocket mass. Okay, so I'm going to let delta M to be a change in rocket mass. So what do I mean? So hang on, M1. I'm talking about M1, right? So wait. So I'm sorry. I mixed up my labels because I call this V1, right? I should be consistent and call this V1. And if I call this V2, I should be consistent and call this V2. Okay? So yeah, I'm sorry. Just changing the labels. But delta M is the change in rocket mass. Therefore, delta M is the final rocket mass, and delta M is the this M is the initial mass. Therefore, M2 is just little m plus delta M. Okay, so what I have is little m plus delta M over here, right? So I got M2 already now. Okay, then finally how to get M1? So M1 is just in terms of the other things, determining M1. Okay, so how to get M1? Well, basically we expect that the total of this thing, well, previously they are inside each other, right? So previously they are together as M, then after that they got separated. So we start from the fact that of course M1 plus M2 is just M, right? And then I want to express this in terms of M1. So M1 is just M minus M2, and then also we know that M2 itself is this. So therefore m1 is just m minus m plus delta m, and therefore we find that m1 is just, these two cancel, I got delta m, right? So I have finally figured out m1 and m2 as well. So m1 is just negative delta m. So does anyone follow or agree with this formula so far? How to compress air? You can use a pump. Bicycle pump may work fine. Why not negative delta m? But it is negative. What do you mean? It is negative delta m. Right? Yeah. So yeah, so this one is negative. And then also because m1 plus m2 should be m, right? So this will, if I plus this, this will cancel, so you really get m. So everything is consistent over here. Okay? Does it only hold after inertial frame? No. For non-inertial frames as well. But we okay, so that's inertial frame. Okay, so for our purposes, as it holds as long as there is no external force, right? If you have a accelerating frame, that means there's going to be some equivalent force acting on it. So in that sense, it might not be conserved. But if you account for it, okay, then the momentum is conserved. So so I think, yeah, for to answer Eric's question, for the purposes of this course, yes, it only holds under the inertial frame. If you for the momentum, we define mv, right? Total momentum mv. Because if you go to more higher level physics, we actually define a different version of momentum which is conserved regardless of what happens. Okay. Okay. Not only what time is it now? Okay, 33. So everyone agrees with, okay, so everyone is like okay with how we get all this, right? Then the rest is easy already. The rest is just plug in. Since everyone is okay with how to get this, then conservation of momentum is just the mv is conserved, right? So mv is conserved. So let's try to work this out. Okay, so we shall do that. Full screen. Okay, so conservation of momentum, right? So that's what we're going to apply. Conservation of momentum. Okay. Yes, so conservation of momentum, well, this is my initial momentum, so I got mv, right? So this is my initial momentum, and then after this I have these two objects now, so I got m1 v1 plus m2 v2, right? Okay, so no problem there. And then I have all the formulas for m1 and v2 everywhere now, so I can substitute inside. We have calculated m1 to be delta m, and then v1 is v minus vex, and then m2 is m plus delta m, and v2 is v plus delta v, right? So let's try to expand this and see what happens. So if I expand this, I got v delta m, and then minus minus plus, I got vex delta m. Okay, I prefer to put delta at the back, and then I got an mv here, and then I got an m delta v here, and then I got v delta m here, and then dm dv over here, right? So notice that mv and mv will cancel each other, and then there's a v delta m and a v delta m which also cancels each other, right? So what I have left is just vex delta m, and then plus m delta v is plus dm dv, delta m delta v. Okay, so from here I'm going to take the limit and then get a differential equation over here. So what I will do is I will take this to the right. So this is a negative delta V, and then I got Vex delta M, and then delta M, and then delta V. Okay, so now let me divide both sides by delta M, and then also might as well bring this down also. So I got delta V and delta M is equals to negative Vex over M. So divide M, so this one will become 1. Divide, it will become delta V. Okay, and then now I can take the limit. So notice that, right, as delta M, as there's no change in mass, there should not be any change in velocity. So that one we know. We know that delta V goes to 0 as delta M goes to 0. So this limit will be some number, and it will turns out to be a derivative, right? So if I take this limit, and then delta V will just go to 0 here. So therefore, we take the limit of delta M going to 0, dv dm, and on the right hand side is taking the limit of delta M going to 0 of all this stuff. So therefore I got delta V, but in this limit we know that they will be 0, right? And what does this mean? So this means dv dm, right? So this is dv dm, and on this part is just Vex over M plus 0. Okay, so I got a differential equation. This is dv dm is equals to negative V over M, V exhaust over M. So V exhaust for our purposes is usually a constant, right? It's the speed of the fuel coming out relative to the rocket. So it's based on the rocket design, it's based on the rocket engine. So it's going to be constant throughout the motion. So this is our rocket equation. So the Vex will be constant, but the M will not be a constant because the rocket keeps losing mass. So the mass of the rocket will be less and less as the rocket keeps on ejecting fuel. Okay, so this is our rocket equation. Does everyone follow so far? Why delta V is 0? Yeah, so if there's no change in mass, that means no change in mass means what? Means no rocket ejected. The rocket stays the same mass, so it doesn't eject anything. So if it doesn't eject anything, means it's not doing anything. If it's not doing anything, the speed will be the constant. So delta V is 0. Okay, makes sense? Okay, any other question? So if no question, then the next thing we're going to do is we're going to solve this differential equation. So yeah, differential equation. This one is quite easy to solve. Okay. From delta V, delta M. Cannot follow. Why? You mean this one? This one is the calculus, right? This one is the definition of the derivative. Then on the right hand side, if you take the limit, this is independent of delta M, right? So this is about the changes of mass. This is the previous mass of the rocket. So you got this. Sorry. So this last term at the back will become 0. So yeah, what I was saying just now if so the delta, right? Delta means changes here. Okay, this is change in velocity, this is change in mass. If the mass doesn't change, the velocity doesn't change. That's all I'm saying, right? Nothing special there. If the mass doesn't change, then the velocity doesn't change. The mass doesn't change means what? You turn off the rocket, right? You just shut down the rocket, so you don't do anything. Okay? Okay, so yeah, basically the delta is the changes. Okay. So what we can do next is to solve this differential equation. Okay, so let's try to solve. Everyone clear? Is it okay? Charles? Should be fine, huh? Okay, so yeah, so what we're going to do next is to solve this differential equation. well, separation of variables. There's a m here, there's a dm here. So what I can do is, I got dv, and then I will bring the dm over. So what I have here is minus vex over m dm, and then I can integrate dv, right? So nothing special there, and then we can easily integrate. So let's say my initial mass of the rocket is m0, and my initial velocity of my rocket is v0. If it starts from rest, then the whole thing is 0. But yeah, we can be general. And then after, at a later time, it will become the mass m, and then it will have a corresponding velocity v. Okay, so if I integrate both sides, I got v minus v0. Vex is a constant. So if I integrate 1 over m, I just get ln m, right? So I got m0 over m. Basically, it's just vex logarithm of m over m0, right? So v is equal to v0 minus vex log of m over m0. Okay, so this is the solution to the rocket equation, right? So what happens is that, what happens if I plot the v against m? Okay, so if I have m here and then have a v here, my m0 is starting at some initial number, which is the full initial fully filled rocket, right? Fully filled rocket. But if I plot the graph, it's going to look something like this. Okay, so yeah, my handwriting is very ugly. So initially I have some initial velocity, but if I burn off more and more fuel, it's going to go higher and higher speed. Okay, according to this equation over here. So after you burn the fuel, right, this mass will be lower than the initial mass. So this will be a ln of a number less than 1. Ln of a number less than 1 is negative, it will cancel. So this term is positive. Positive, it will raise up the velocity of the rocket. Okay, so is everyone okay? Everyone still clear about the delta m, dm, dx, vex, everything? Does the field have maximum mass? We do not take this into account. So the maximum mass shall be the initial mass, right? And it depends on how you build the rocket. If you start with a water bottle, it's probably like 1 kg or something. Right, if you start with a rocket, it will be how many thousand tons. But that's just how you build the rocket, so that's not what we are calculating here. But it will lose mass, so it will be lower and lower mass later. Right? Yeah. Oh, yeah. So that one, yes, that one is something that you need. We have not taken into account. So, yeah, because right, we are not including gravity, because so over here, right, I make it fly horizontally. So I did not take into account how to overcome gravity. But you're right. So in order to overcome gravity, then the force of it must overcome the gravity, right? So yeah. So which is the next slide over here. Okay. So you can actually calculate the thrust force, right? So if you use the Newton's second law, if my rocket is going vertically, right? So now if my front of the rocket is pointing upwards, okay, it can overcome the weight of the rocket due to gravity. So the thrust force is like F is equal to ma, and then acceleration is dv dt. Okay, but if you do the change in variables, so I got dv dm, dm dt. So from here I got m. Oh, switch full screen, sorry. Yes, do you know why? Because this m, right, after you burn the rocket will be lighter than how it started, right? You burn off the fuel already. So it's a smaller number dividing a larger number. So smaller number dividing larger number, ln of that will be less than 1, 0 point something something. So ln of this will be negative, the logarithm. Okay, so yeah, so we got here. dm dt. So I got over here v exhaust dm dt. Okay, so this is what we call the thrust force. Okay, so if I want to make it fly against gravity, right, let's say my rocket is now going up, right, so the thrust force will make it go this way, and of course we want to overcome the weight of the system. Yes, yeah, that correct, Charles. That's what I was saying. Well, not to say the final mass, because the mass keep on changing. So at any instant moment, right, this m is lower than the previous one, and then it keep getting lower and lower. It's not just the final, but it will slowly or fastly get lower and lower than this m1. So m minus m1 is smaller than 1. So the ratio will be smaller than 1. Okay, I don't need the modulus because both are positive numbers actually. Yeah. So the ln of m over m0 will be negative. Okay. What's the time? Okay, so let's I have about 13 more minutes before we break. Let's see, got any more question? No, so this is the rocket, right? So the thrust force will tell you the force that is pushing on the rocket as it burns the fuel. And this part is a bit more complicated, is because the mass of the rocket is not a constant. Okay, but we try to assume that for that instant, ma, for when the instant the rocket has this mass, then it will have this acceleration, and at that instant, okay, it will have dv dm times dm dt. So this is the instantaneous thrust force experienced by the rocket. So this is how we can calculate, right? So, and this one will be used to overcome the gravity, the weight due to the gravity. The fuel mass will not affect thrust force. The fuel mass itself, no, but the dm dt, yes. Okay, so what is dm dt? The dm dt is the rate of fuel mass being ejected. Okay, so it depends on the rate of it being ejected. So that means, like, if you burn the rocket more powerfully, right, the force is stronger, and the reason why is because more fuel comes out. So there's many kg per second of fuel being ejected, so that the rocket will experience a stronger force to push forward. Okay, yeah, any other question? Okay, so before we run short of time, let me cover the next thing, which is about the center of mass. So I guess today we cannot start on rotation yet. We will do that on Monday. But let's talk about the center of mass. Okay, so 4.6.1. Let's talk about the center of mass for the collection of point particles. Okay, so let's say I have many particles, right? I have object of mass 1 going at velocity 1, and then object of mass 2 going at velocity v2, and then some other mass going at some other velocity. Okay, and there's many particles over here. So for this whole collection, right, you can treat this as one system, and that is what we shall do, and that is where we start to get the concept of the center of mass. Although many of us, in the last few classes, we already mentioned center of mass many times, right? Right now, let us derive exactly where it comes from. Okay, so what's the center of mass about? So the center of mass is about this. Okay, so this is many particles. So let's consider what is the total momentum of the system. Okay, so the total momentum of the system is basically just add up all the individual momentums of everybody. Okay, so let's say if I have n particles, then I will have n momentum, so I have add up all the terms there. Okay, so nothing special over here, but firstly let me just write it like this. So velocity is the rate of change of position. Okay, so let me write this in terms of the rates of change of positions for everybody. Mn drn dt. So this is the rate of change of positions of all the particles, right? So this is equation 1. What is center of mass about? So center of mass, right, is to pretend like instead of considering a system of many particles, let us replace and imagine another system with just one particle. Okay, so we are going to imagine this total momentum we imagine that it is imagine that this total momentum is carried by an equivalent system that is consists of an imaginary single object with total mass m, which is just the sum of all the masses. Okay, because we want to change this by imagining a separate system with just one object, but we want to maintain information about the previous system, so we say that the mass of this new object is the same total mass as the whole thing. Okay, so therefore the total momentum of this system will be carried by object of this total mass having some velocity, which I write as capital V. And right now I don't know what is the correct capital V to replace, but it should be the equivalent rate of change of an equivalent single object. So my equivalent single object is, I imagine, is just some big M and moving at some overall velocity V. Okay, so this is like this. Okay, and I want to purposely imagine them to have the same momentum. So if I compare equation 1 and 2, okay, so I got M, this is dr, I write this in terms of dr dt, and on the right hand side is all the dr dt is over here. Right, up till n particles. Then I got this equation, right? So all this is just constant dt, constant ddt, constant ddt. So if I integrate both sides, I just have r. m1 r1, m2 r2, dot dot dot, mn rn. Okay, so what I have now is that I have a formula that tells me the position of this imaginary single object, which is my center of mass. Okay, so it's just m1 r1 plus m2 r2 dot 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 plus mn rn, and then dividing by big M, but big M is just the sum of the masses. Okay, so I got this now, right? So yeah, so this is the formula for the center of mass. So we will call this equivalent single imaginary object. The center of mass. Okay, and R is the position of the center of mass. Okay, it's a position vector. Position vector, it just means it has an x and y component. Okay, so any question so far? Okay, so okay, so now is a good time to take a break. So let's take a 5 minutes break, and then we will come back. We will continue with the tutorial. Okay, and actually I do need to cover more topics for the continuous bodies. But let's see, let's come back from the break first. Okay, so let's rest for a while and then let's see. Okay, so let's take a 5 minutes break. And you can ask me questions here in the meantime. If you can hear if you can hear my sound, right? Hang on, let me stop the recording first. Then I can play the video. OBS, stop. Test. 1, 2, 3, test. Yeah, we shall see in a few hours or in a few days, because some states say they need the result will only come in by Friday, so we shall see. Okay, so let's okay, so I'm gonna work on some tutorial questions, and if there's enough time left I will continue the center of mass discussion. Is that okay? For the tutorial question, there's definitely one question that everyone wants to do, which is question 6, right? So I'm gonna do that. That's the important one. And then after this I will upload the solutions for the other questions, and I want to try to cover the syllabus before the midterms, right? And also because before the final exam, so we need to make sure we cover the syllabus. So in any case, everyone is back now. Let us get started with tutorial. Yeah, bring up the tutorial 3. Okay, so I believe this is the question that everyone wants me to do, right? I will upload the solution, but still, this is the tricky question in tutorial 3. Am I right? So this question is talking about a pendulum comprising a string of length L. Okay, everything fine so far if it's a pendulum, but then there is something blocking the pendulum. So there's a peg, right? So there's a peg, and so it hits this peg as shown below. So we need to solve two things, right? So the first thing that we want to solve is to show that the sphere is released from a height below that of the peg. It will return to the same height. So this part is still easy. So this part is still, hang on, let me. So part A is just concept wise, right? So how to show? Well, the first thing to notice is this, right? Full screen. Okay. The thing to notice is that well, how do we show that the pendulum will return to the same height? So, well, first thing to note is the pendulum will return to the same height if there is no energy loss from the system, right? If there's no energy loss from the system, mechanical energy, right? And we have learned that energy will be lost from the system if there is no non-conservative forces, right? So so energy will be lost if there's non-conservative forces. Okay, so now let's think. In this pendulum, is there any non-conservative force acting on the system, especially when it hits the peg? Right, so when it hits the peg will exert the force on the system. Okay, and then also, of course, this pendulum is swinging under gravity, so the forces acting on the pendulum well, the first one is gravity, and the second one is from the peg. Okay, so yeah, is the whole world is becoming this right now? Yes, Chengming? What's up? Okay, I think Chengming is about to say something, but meanwhile, So let's see whether this will lose any energy or not. So the gravity force is conservative, right? We calculated the potentials and everything, so this is conservative, so no problem. This one, it's not really conservative, but the main point is that if the force coming from the peg, right, this force is not moving, you know, peg is stationary. So the stationary peg doesn't exert a force across a displacement, so there is no displacement over here, so there's no work done. Okay, so there's no work done. Even if there's a non-conservative force, this work done is zero, so there is zero force acting onto the peg. Full screen. Oh, I'm Malaysian. Yeah, I'm Malaysian, but now it's full screen, right? Full screen, yes. Yes, I'm Malaysian. I'm from Perak, but I was living in Singapore for around 13 years. Yeah. So I spent a lot of time in Singapore, so I got a lot of Singaporean friends. Okay, so yeah, so the non-conservative work done is zero. So then this is conservative, so there's no energy loss from the system. Okay, so no energy loss, so it can return to the same height, right? It has enough kinetic energy to come back to the same height, right? So that is the how we show part A. So part A is still like conceptual type of questions, right? 13 years of bad food. No, okay, so the thing about the food, right, Singapore versus Malaysia is this lah. Malaysia, the food that we like is those, you know, hawker shop, you know, wanton mee, all those chicken rice kind of thing. But in Singapore is where you can find like international food. If you want to find like good Middle Eastern food, Indian food, Italian food, French food, you can find it there, although it may be expensive lah. So that's the difference between the good foods that you find here and the good foods that you find in Malaysia, right, and Singapore. Yeah, in Malaysia you cannot find like good French food, you know, and this is the kind of thing I miss about Singapore. Okay, so drawing the diagram. Okay, and I have a peg, so I'm going to solve part B, right? So what is the minimum distance that you need to the integral? Oh, the integral is just nothing. I just mean that the peg is not moving, so work done, right, is force times displacement. The peg doesn't give a displacement, right? So even if there's a force exerting on the pendulum, there's no displacement by the peg, so the work done is zero. So the work done by the peg is zero. Okay, that's all I'm saying. Yeah, I mean the integral is just, I'm writing something there only, nothing special. Okay, so so this is my peg. Okay, and then I want to calculate what is the minimum distance d of the peg. So the distance d is my peg over here, right? And then my pendulum swings. Okay, so the pendulum swings and then coming until here. Okay, so let me call this position 1, and then this is position 2. Okay, and then let's keep track of the changes in height. So when my peg is here, right, it will undergo a circular motion where the radius is L minus d. Agree? Right? So this is the total length of the peg, and then reduced by d, so this is the radius of the circular motion. So this is L minus d. Okay, so that is one thing. And then the next thing is the pendulum, right, it starts from rest, so initial speed is 0. So in going from here to here, it changed height, so we can calculate the change in potential energy. So what is the change in height? So the change in height, right, of the pendulum is, well, what is this changing in height? So this part is d, but this part is L minus d. So so it's actually d minus L minus d. So this is actually 2d minus L. Okay, so this is how I can get the change in height. Okay, so everyone follow so far? Right, I haven't started calculating. We just need to calculate what is the condition so that this peg can continue swinging in a circular motion. Right? So, yes, Charles, no energy loss, can return to the same height. Yeah, well, there's another factor, you know, Kaheng. In Singapore, salary is higher also. That's why. Yeah. Curry chicken, actually there's a curry chicken place that I do like in Singapore. Yeah, there's good food there lah. Even the curry chicken and chicken rice, but you need to find. It's very hard to find. The standard ones are not as good. Campus food. Oh, campus food in NUS, there are also some good ones and some bad ones as well. I miss the roti canai there. Okay, so now how to solve this problem? We need to use conservation of energy, and we need to draw the free body diagram. Let's start with conservation of energy. Okay, so from here to here, we have shown that the peg doesn't lose work from the system, so we can apply conservation of energy. Okay, so by the conservation of energy, well, our starting position at position 1 is I have 0 kinetic energy, but I have the potential energy at height 1. Okay, so height 1, I'll keep it like this first. I just need to know the change in height, right? So by the time it comes to here, right, I will have some kinetic energy, so half mv squared. So this, at this point, the pendulum will be traveling at velocity v, and then the energy at this height will be the height 2. So what I got now is half mv squared is actually the change in the potential energy, which is height 1 minus height 2. In other words, height 1 minus height 2 is what I'm trying to say is delta h. So mg, delta h, and delta h is 2d minus l. Okay, so we can actually get the formula to derive the formula for v2 at this height. So v2 is 2g 2d minus l. Okay, so let me put the 2 inside, so I got 4d minus 2l. So v squared is equal to g 4d minus 2l. Okay, so this is my first equation. Okay, are you guys still complaining about food? Oh, yeah, XMUM food, you guys don't like, is it? That's okay. Yeah, and even in the area around XMUM also not much good food. Yeah, the Malaysian good food you cannot find around the campus, unfortunately. So after you have found the conservation of energy, then what is the next thing to consider? Okay, how can we make sure the pendulum swings one full circle around the peg? Okay, I need some props over here. Okay, so I have some pendulum, right? I hit the peg, and then I want to make it go to a full circle, right? So to make sure it goes in a full circle, I want to make sure it goes in a circular motion. And to have a circular motion, I need to have a centripetal force. So to have a centripetal force, right, the only force that is acting towards the center is, well, there's a tension acting towards the center all the time. And then there's also a weight, but the weight has the components. Okay, so now if you want to make sure it goes to a full circle, right, the tension must be non-zero, right? Tension 0 means what? I mentioned this last time, right? Tension 0 or negative, it means that the string has loosened, right? So it means the string has loosened. So I need to make sure the tension is always non-negative, greater than 0 at all times. Okay, cannot be 0 or less, because once it becomes 0 or less, the string will loosen. So I want to make sure that the tension is non-zero. Okay, so let us calculate. The most dangerous part where the tension may become 0, right, is when it's at the top, right? So at the top is the part where the tension is the weakest. So if the tension is not 0 at the weakest position, then we can ensure that the particle can make one full circle. Okay, do you understand so far? Yeah, you feel sorry for your mouth because in XM you only eat for sustenance. That's what most of us end up doing, right? Yeah, chap fun to save money is the cheapest. For the lowest price, you can get like different types of variety lah, so you don't get sick of the food, right? With the chap fun every time. So what I'm going to do is, we are at the top of this. I want to draw the free body diagram at position 2. So position 2 is where the particle, the tension will be the weakest, and it might go to 0 there. So we need to make sure the tension is not 0 there. So we draw the free body diagram at position 2. Okay, so free body diagram at position 2. So position 2 is at the top of the circle. What are the forces acting on it? Right, so there's the usual weight of the object, and then there's a tension T. Okay, so the forces acting on this is mg plus T. So this is a radial force, so this is a centripetal force. That means it is equals to mv squared over the radius of circular motion. But the radius of circular motion is just L minus D. Okay, so what I have here is mg plus T is equals to mg m over L minus D v squared. Okay, so hang on, yeah, okay. So mg L minus D. The mosquito is disturbing me. This, okay. So this is equation 1, right? Basically, right? Now I have this equation 2. Okay, so I have equation 2, and then there's a v. So what I can do is I can substitute this v into here, right? So let us do that. We'll substitute equations 1 into 2. Okay, so I got mg plus T is equals to m L minus D, and then the v is g 4d minus 2l. Okay, so I substitute this in already. And from what we can see here, right, is that if I change my position D, I will change the tension. Okay, so we are looking for the worst position D, so that the worst case scenario, so that the T goes to 0. So then we can determine the minimum D. Okay, so when the distance is the minimum distance D, the tension goes to 0. So I want to calculate this case. Okay, so I want to calculate this case. So that means in this situation, I got m L minus D, and then g 4d minus 2l. So when this is 0, I can cancel the m, right? And then I bring the L minus D out. So I got g L minus D is equals to, I can cancel the g also, 4d minus 2l. Okay, so cancelling this, and then I got L minus D is equals to 4d minus 2l. So if I bring this there, I got 3l is equals to 5d, and therefore d is 3/5 L. Like this. Okay. Any question? Do we have Subway sandwich? No, not in the campus. Yeah, although somewhere elsewhere in Malaysia they do have lah. Yeah, another thing about the when the university in Singapore that I went to, right, they have a Subway inside the university, which is very nice. They have Subway and McDonald's inside the university. At one point they have Wendy's also, but they closed down. So everyone okay with this calculation? Accelerate my hand towards the mosquito. Unfortunately, I missed it. I didn't hit the mosquito. By using the inertial frame, you're talking about the mosquito, is it? Yeah. So which part to repeat? Okay, so so I repeat the idea. I think that's the important thing, right? I want to make sure that the pendulum can swing in a full circle, right? So in order to swing in a full circle, right, the string must be tight. Okay, it cannot loosen. Okay, if it loosen means it's no longer circular motion, it will just drop. So in order to make sure it doesn't drop, the tension must be tight. That means the tension must be non-zero. Okay, so what is the minimum distance to have tension non-zero? That is what we want to calculate, the worst case scenario. Okay, so from this picture, right, if I increase this minimum d, so if I lower this too much, right, then there's a chance that the tension will become zero as it passes the top. So that is what we want to calculate, right? Tension must not be zero. The worst case scenario is close to zero, right? Close to zero. Then any worse than that, it will drop. So that is our calculation. So by using conservation of energy, we can calculate a formula for the velocity at the top part. So the top part is where the pendulum will start to drop. Okay, so we need to make sure the pendulum doesn't drop there. So let's see what happens at the top part. So to see at the top part, right, over here we draw the free body diagram. It is a circular motion, fine, right? So the radius of the circular motion is L minus D, also fine, right? But there's a V square. So V square I can substitute from equation 1 over here, right? So substituting equation 1, I got this expression. So this is where we start to consider the worst case scenario, right? So as long as t is positive, fine, no problem, right? But the worst case scenario is where t goes to 0. So when does t goes to 0? At the worst possible d, right? At the last possible d. So we put these conditions inside, right? So we put this condition inside, and then we simplify, right? So after we simplify, we will get 3 over 5L. Okay? Yes, mg plus t is the centripetal force, yes, at the top. And then what's EK? Kinetic energy. EK. We can't, right? We can't, because if we just use energy alone, it doesn't tell us the information. We did use energy here, right? Conservation energy, we just get the formula for V. But based on the conservation energy, we can't tell whether the tension is 0 or not on the top, right? So only by free body diagram we can make sure when does the tension goes to 0. Yeah, I think by answering Zirui, I answered this question without using circular motion. Yeah, just now, yes, as I was saying, right, just by using energy alone, that's all we got, right? We just get this formula. Then it doesn't tell us anything about whether the tension goes to 0 or not. Is the tension 0 on the top, right? Okay, so everyone's fine? Okay, yes, great. How about everyone else? Is everyone else clear with the solution? Okay. Yes, you're right. We must know the T of the rope and make sure it's positive, or the minimum D will be the 0 case. We must know the T. Okay. Clear. Okay, so now what to do next? Is there any other tutorial question do you want to do? Because I kind of want to finish off the center of mass. So the urgent tutorial question we have finished already, and I will make use of the time to do 4.6.2. Okay, so I think it's because the midterm is getting nearer and nearer, right? So I think it's a better idea to continue with the lecture first And then as nearer the midterm, then only we spend more time doing questions, right? Rather than the other way around. So let's talk about this first. Okay, no objection? Okay. Everyone clear? So let's talk about center of mass for the extended bodies. Now for the non-extended bodies, right? For the collection of particles, the center of mass is just the summation of all the points like this, right? But if it's an extended body, then it's like you can't treat it like a point anymore. It's one huge thing. So what do? Right? The formula that we do have is for points. Is this point, right? So what we can do is, we can cut this up into many pieces. Okay. So I have one huge object. What is the center of mass? Right? So if I cut this up into many pieces, then I can treat this as many points. So maybe I can still apply the points formula over here. Okay? But as you have learned from calculus, right? These are many points with many tiny mass. So if I sum up many small things, it will become like an integration. So this is what will happen here. So let's look at one particular object, one particular point. So this point has a particular mass dm, and it has position r, right? So position r relative to some coordinate system. Okay, so if this is the dm of the system, so dm is an infinitesimal mass. Okay, dm. From dm, we can actually get the total mass, which is the total mass of this object, right? It's just the integral over dm. Okay, so this is for the mass. Then how do we get the center of mass? All right, so the original formula for center of mass that we previously have is the summation of points. Okay, but this is many infinitesimal points, so it will becomes like a integration, right? So I got r dm. Okay, so in other words, the formula for the center of mass is take 1 over m, right? And then you integrate the position vector of the whole thing with respect to dm. Okay, so yeah, I just introduced the concept, right? So I can't ask if you have any question, but are you guys feeling scared of this formula now? Right, so this is the point where the students who are not familiar with the, oh yeah, okay, now only I saw no objection. Okay, thanks. So slightly scared of the formula. Okay, don't worry, I will show you how to use it. The thing about this, right, most of the time physics formula, they look scared just by the appearance only. Then when we realize to actually use the formula is a very standard method, right? And then the standard method can be applied to many different situations. So once you learn the standard method, it won't be so scary anymore. Okay, so I will show you, right? So I will show you how to do it. Math sucks. Oh, but you are taking math also, right? Calculus and linear algebra. So midterm test, is it open book? Well, let me put it this way lah. Most likely we'll do it online, right? It's in your own home, and I can't go to your home. Yeah, math is the life of physics. That's true. Okay, so that's true. Yeah. So let's see how to use the formula by working. Oh, before, okay, it looks scary because first of all, it's in vector form, right? It is appearing in vector form. But remember, right, vector, it just means x and y components. So that means for the position, I can get the x coordinate for the center of mass. It's basically just 1 over m, integrate the x variable with respect to dm, and I get the y coordinate of the center of mass, I just need to do this, integrate y with respect to dm, right? So from these two, I can get the RCM is just the x component after you calculate, and then the y component after you calculate, right? So that's all it means by having the vector. Okay. Engineering math 1. Go slower. Okay, yeah, I've been wasting time talking about math. Yes, well, the calculus is taught from the math perspective, which is, I think there they do not apply much to physics problem. Yeah, so I don't know how to read that. So, okay, go slower. But nothing much. What is just the formula is the scary formula. Then I just telling you that, okay, RCM has x and y component. So this is the x component, then this is the y component. Okay, and actually it's very abstract now. So it's hard to understand at this stage. So let me work out an example, then only you know. Okay, so how do we find the center of mass with a rod? Okay, so let's say I have a rod, a uniform rod. Okay, uniform rod. Oh, okay, yeah. So I use physics to secretly teach math or something like that. Yes, I get what you mean. So how do we find the center of mass of a uniform rod, right? So this is a uniform rod. Uniform rod means mass per length is the same for the whole rod. Okay. A non-uniform rod is like maybe this part is higher density, so it's more materials there, and then on this side is lighter, so it's not uniform. But uniform rod, everything is uniform, right? So if it's a plastic ruler, the whole thing is plastic, same material, same density. So let's say this is my x0 and this position is x equals to L. This is my x-axis. So the length of the rod is L, and m is the mass of the rod. Okay. So how do we find the center of mass of this rod? Okay, where is the center of mass? Right. So where is the center of mass? The formula that we want to use is over here. Okay, so we need to work this out. Well, we need it looks scary because this is an abstract form. What we need to do is, how do we integrate dm? We can't really, because this is variable is x, this variable is m. We need to change and make sure everyone is the same variable, then only we can integrate. Okay, so how to do that? Well, first of all, right, we notice that this is a uniform rod. Okay, and this is a dm. So let's imagine some position where I take a small piece. So this small piece will have a small mass dm, and the length of this is a very short length dx, infinitesimal length divided by infinitesimal length, right? So if I take this small piece out, right, then I can find the mass per length of this rod. Okay, and because this is uniform, it will be the same answer if I take the total mass divided by the total length. Okay, it's just the mass per length, right? So mass per length is the same for the whole rod. Everyone agree, right, so far? Okay, so what I'm going to do is, well, I will do this and take the dx here. Okay, so I'm going to do this next, right? So this is the this is a formula to express dm in terms of dx. What part you don't get, Charles? Okay, so dm, okay, Charles, dm is the, for anyone who don't understand, right, beside Charles, dm is the mass of this tiny piece, right? and dx is the mass of dx is the length of this piece. Okay, so what I want to calculate is the mass per unit length. So I take mass per unit length. Okay, so it's some kg per meters, right? So it's some number of kg per meters. So I get the density of the rod, the length density. Okay, yeah, so that's what I'm saying now, right? So I got this. Okay, so this is the mass per length of this rod. But since this is a uniform rod, right? A uniform rod, well, if I take the whole mass and divided by the whole length is m over L. And if it's uniform, this number should be the same, right? If it's made by plastic, plastic is how many grams per meter? So it's the same number. Okay, so these two numbers are the same, right? Then okay, so Charles agrees, everyone else agree, I hope. Then after that, I just manipulate this equation. I bring this to this side, right? So let's check if my formula is correct. Okay, if my formula is correct, right, well, I can derive my total mass by doing this. So let's see if I dm is given by this substitution, so dx, and then I change this into my x integral. So my rod goes from 0 to L, therefore I integrate from 0 to L. So after I integrate this, it's just L. So I cancel this. Yes, it's consistent. Okay, so this formula is correct. Pure element better. Okay, yeah, silver or gold. Then it's more fixed density, right? That's true. Okay, so I got this formula now. Okay, so now we are ready to find the center of mass. Okay, so what I want to do is I need to calculate this thing, and then I want to integrate. I just need to apply this. Hang on. I just need to apply this formula. Right? This is dm. Right? Let me write one more time to avoid confusion. Okay. Okay, so how do I use this formula, which is the scary looking formula, but actually this is the method, right? The method is, firstly I need to think about this. Once I got a formula, so the step one is to express dm in terms of dx. This is step one, right? So I expressed this already, and then this is my formula. So step two is to substitute this dm over here. So this is step 2. So once I got this, now what do I get? 1 over m, and then I got integrate this, and then I substitute this whole thing, so I got m over L dx. But m and L are just constants, right? And in fact these two will cancel, so I got 1 over L integrate x dx. Okay, so I change this into an integral, and then to integrate, I need to think about what is the limit to put in. Well, the limit is where the rod is. So the rod is between x0 and x equals to L, right? So I need to make sure I cover the whole rod. So when I integrate from 0 to L, right? So I guess this is step 3. Step 3 is the limits. To put in the correct limits. Okay, but once I put in the limits, I can perform my integration. So I got 1 over L integrate half x. Integrate this becomes half x squared, go from 0 to L. So it's 1 over L squared over 2. Cancel this. I finally got the answer is just half L. Okay, so the position of the center of mass of this object is half L. Okay, which is for a uniform rod, right? Yeah, it's right in the middle. That means it's in the center. Is actually at the center of the rod, center of mass, right? So it's L in the middle of the rod. So L over 2 on both sides. Wallet not allowed. Yeah, I mean, yeah, you can't just get gold lying around anywhere, right? So does anyone follow so far? Everything okay? Okay. Yeah, because this is theoretical, right? So theoretical, we can just say it's gold, but we don't actually have to buy gold. And that is the advantage of theoretical physics over experimental physics. Right? So if you work, so if you if you become a physicist in the future, right? You either become a theoretical or experimental. And if you're an experimentalist, you need to worry about money all the time. So that is the unfortunate thing. Okay, so there's a bit of time left. Let me just like demonstrate one extra thing to see how to use the formula. So what if rod is not uniform? Okay, so this is the question, right? So what if the rod is not uniform, right? So if the rod is not uniform, right? Okay, so it's still the same thing. So I still put my left side of the rod at 0 and this part is still L. Okay, but let's say you are given. Okay, so let's say you're given that the mass per length of the rod is equals to some constant and then is linearly dependent to x. M is total mass, yes. M is total mass. Total mass of the whole rod. Okay. So everyone follow so far. I'm going to the next question now. It's not in the lecture notes, but I purposely solve a slightly different example so that you understand how to use the formula. Okay. So a question will give you this. Okay. A question will give you this, right? dm dx equals to this. So what is this? Where the lambda is some constant. So some positive constant. So that means when x is 0, the density is 0, right? When x is higher, the density is higher. So that means what this equation is telling us is over here is having a lower density. And then over here is a higher density. Okay. So this is some constant is given, right? Maybe in a question they will give you a number, right? 0.5x, right? Let's say. Okay. So what is the total mass of the system? Right. So oh yeah, by the way, before total mass, I need to express step 1, right? So dm is equal to lambda x dx. So to get the total mass, I just need to integrate the dm, right? But I do have the dm formula already, so I put it in here, right? So I got integral of lambda x with respect to dx, and then to make sure your integration is correct, I need to go from the correct limits, right? From 0 to L. So I got this now. So what I have is x squared over 2 from 0 to L, and I got lambda L squared over 2 m. So therefore, this is my total mass is lambda L squared over 2. Okay, so my total mass depends on this lambda. Okay, so that is one thing. But where is the center of mass? Right, so where is the center of mass? So the center of mass is, I need to use this formula now. So 1 over m, right? And then I integral x with respect to dm. So that is the dm I need to substitute as well. So dm, I put this into here. Right, in fact, my m also I can put it here. The density would change with x. Yes, Jerry. I'm just purposely randomly think of a question, right? What if you are given a rod that has a non-uniform density? So the density changes with x. Yeah. So this is a given situation, right? So let's say you are given this rod. So where is the center of mass? Okay. So let's try to figure this out. Well, after I substitute m, so this is lambda L squared over 2, and then the integral, right? So if I put in the dm, I got lambda x dx. Okay. So what I have now is this is 2 over lambda L squared, and then the lambda I take out to the front, so it becomes a x squared integration. Okay. So that means I simplify my problem into this. So I got the lambda will cancel. So I got 2 over L square integral from x square with respect to dx. Right? Follow so far? 3/4. You calculated the answer already? I don't know what's the answer. I think it could be 3/4. Let's find out whether Zirui is correct. Well, to find out, let us put in the limits of the integral, right? And then 3 over this. So if I integrate, I got x3 over 3 from 0 to L. So if I substitute in the limits, I have 2 over L square, and then I got L cubed over 3 minus 0, right? The lower limit is 0. Okay, so I cancel L2 and cancel this. So the answer is not 3/4 but 2/3 L. So XCM is 2/3. Okay, so XCM is 2/3 L. So that means the center of mass, this is the halfway point, 1/3, so 2/3. So my center of mass is like rough, I don't know, like just to sketch, is somewhere around here. If something, if average is about a triangle, what do you mean? Oh, if you talk about a triangular shape, yeah. Yes, so that one is a different story. Yeah, so here we're just talking about the like different, so maybe like the function here is different, so it's different situation, right? So yeah, so the answer here is 2/3 L. Okay, for this case. So yeah, so we finish center of mass, and yeah, so I think the next topic shall be on Monday. We will start on the rotation already. Yeah, so I want to make sure I finish this, because the rotation chapter will be a harder chapter for everyone, and we might want to prefer to spend more time talking about rotation rather than spending too much time talking about momentum. Okay, and yeah, so that's it for the momentum. Does anyone have any other question? Oh, I think, yeah, I've heard of this method, but I'm not very familiar with it. Something about the centroid, right? So centroid, and then from here you find the center of mass. Yeah, I think there's something about centroid. I remember centroid things, and then the intersection of this. Okay, how about so everyone is okay with the center of mass calculation? Hopefully the formula is not so scary anymore after I show you how to do this. Of course, I show you how to do this for a rod. In the lecture notes, there are many other kinds of the center of mass, right? Okay. Oh, I forgot. Did I forget to put the picture? Oh, never mind. I think I forgot to put the picture. I will update and include the picture. So you can find a center of mass of a rod, of a circle, or all those different kinds of things. But I understand that the physics student is only starting to take calculus 1 now, so I will avoid giving you too complicated calculus questions, right? Otherwise, very difficult. When A is constant, in what time? What do you mean? Like when you calculate A is a constant, in what time of the total object goes half of the final x? This, you're talking about collision problem, is it? When A is constant, what is A you're talking about? I'm not sure. When acceleration is constant. Oh, the other tutorial question, is it? The terminal velocity question. it goes half of the final x. Is it the terminal velocity question? Still not very sure. Total time the object goes half of the final x. What is the final x? You're not talking about this center of mass, right? Definitely. Of course, there's no acceleration here and there's no time here. We just want to find the center of mass. Yeah, same calculating theory. Yeah, in a sense that, you know, there's different methods to approach a problem. Then yes. Yeah, so different methods. And yeah, so what you describe is a different method like this. Well, both, yeah, so even if you use different method, you should give the same answer. But I think if you say this, yeah, this is a different question, therefore you get 3/4. So, okay, don't worry. I think I get what you mean. I kind of know what you mean. Like you, it's a different approach, right? Something like different approach, right? But not exactly. But one thing I do mention is this. The difference is that maybe what you're talking about is the two-dimensional object. This is only one dimension, right? So this is only one direction. I am neglecting the thickness and the width, right? So there's no there's no y component and there's no z component. So we ignore the x and y. So it's just a thin rod with only x direction, right? The x and y is negligible, so it's a one thin rod. And when this is a thin rod, you just need to find the x coordinate of the center of mass. Okay. The VT picture. But VT picture is a different topic, right? Oh, the integration. Yeah, I mean, in both cases, is finding the area under the curve. Yes. Yeah. Yeah, if you draw the VT picture, then the area under the curve is the displacement. Yes. Yeah. Correct. Yeah, so if you can formulate it in that way, then yeah, you end up is an area under the curve. Okay, so that's another way to get it. Yeah, so it is, if you look at the formula, it is the area under the XM graph, right? But yeah, something like that. I think so. We won't learn this in 3D, right? Yeah, don't worry, because yeah, 3D you will learn it in calculus 2. So yes, calculus 2, right? There will be a application on multivariable integral. I don't know whether the calculus 2 lecturer will use it or not lah, but in the textbook there are questions about center of mass. So yeah, and well, I will assure you lah, like it is very complicated, but don't be scared, right? Just, you know, follow through the story. And I was last time also when I was a student, like I really hate multiple integrals as well, but once you get used to it, right, it's actually very easy. Not to say very easy lah, it's not easy. Once you know how to do it, then it's not too bad, you know, it's not too bad. As long as it becomes it's just at the end of the day, it just becomes a single integral, but you just need to do it 3 times. So that is the gist of multivariable integral. Yeah, your math MAT classmates maybe can help you lah if you encounter like difficulties with that. Yeah, very easy. Yeah, that is true. So by the way, I think the class is ending already, so if you want to quit the session, it's fine. I'm just talking rubbish now. I'm just talking randomly. Yeah, so Kaishan is right. Calculus is fun when you know how to do it, but the first time you encounter it is scary at first. And the thing to remember, right, is that for humans, unknown things are scary. That's why, like, ghost, even like it applies to everything, ghost story and things. So unknown things are scary, but once you seen it enough, it becomes less scary. So you are more willing to do multiple integrals if you've seen it enough, right? Not to say it gets easier, but you are more willing to try. Charles asking, in PHY need to take Cal 2 and LA2? Yes. Wait, calculus 2, yes. Linear algebra, I don't remember. I think no. I can't remember now off the top of my head. But definitely calculus 2, yeah. We can just easily check the program lah. So please don't ZY again. Why ah? What is ZY? My math is hard to catch up with physics. But okay lah, I think seems like, oh yes, need to take stats, yes. Yeah, good. Stats is important for physics. Yeah, don't be like me. I'm very terrible at stats and then I suffer later. So if you build up a strong foundation, then it's good. Yeah, so since the class is ending, let me stop recording. Okay, we are just like chatting now. So off full screen.